Once we have some data and a model, we would generally want to evaluate how well that model is able to predict the dependent variable, something that we care about. But let's start with a visualization. Let's say that we have our prediction task and have collected some data that we want to use to train our model. That data set likely consists of a set of identifiers, identifying students, assignments, and any other contextual data that is appropriate, along with a set of features that we intend to include as predictors in our model, and finally any labels or columns for our dependent variable. Now, if we train a model on this data, it is commonly the goal that we would want to use that model to predict the dependent variable for another group of students. Maybe I want to use historic data to train a model and predict learning outcomes for next year's students in my class or in a particular school or context. Assuming I have similar data available for these new students, I could potentially do so. The problem is, to find if my model was accurate, I would need to wait until I have collected the dependent measures for this new future set of students, and then see how well my model did at predicting their outcomes. However, rather than waiting, we can simply simulate this evaluation using the original data we had collected. In its simplest form, we can take our original data set and split it into a training and a holdout set that can be used for testing. This evaluation addresses the question of how our model performs when predicting outcomes for samples that the model has never been exposed to during training. The process follows 3 steps. First, we train a model using the features and labels of the training set. Then, we apply the model using the features in the test set to produce a set of predictions. Finally, we compare the predictions of the test set to the actual test set labels and record this as our model's performance. Within this paradigm, it is important that you treat the holdout set just as that. It should be excluded before any modeling decisions are made. This then emulates reality where you don't yet have next year's student data, or whatever context you are hoping to apply your model, to help inform your current modeling decisions. If you did, you wouldn't have to make these decisions. Any changes that you have, or any changes that you make to your modeling approach, to your variable selection, or any other steps in your analysis after seeing the model performance on the test set, runs the risk of overfitting to your current data. That is, changes that improve performance on your current data set may not lead to similar improvements in future data that you collect. So if you see how well your model performs on the test set, and then decide to change something about your modeling approach or the predictors, there's an increased risk that this change might not lead to the same benefit when applied in practice. That said, it is quite common to explore a few different modeling and data variations when evaluating prediction models. So it's important to consider whether the change is likely to generalize to contexts where you hope to apply your model. You want to make sure that you are trying to emulate something that is going to generalize, again, to future data. Toward this, an additional split to your data, acting as a validation set, can help reduce these risks. In this paradigm, we still split the model into a training set and holdout set, but then also split a portion of our training set into a less strict holdout set. With this, we can use the training set and validation set to test our model and make as many changes as we want before then finalizing our modeling decisions and evaluating the result on the true test set. This allows for a more fair evaluation that reduces risks of overfitting caused from peaking at our holdout set, but of course reduces the number of samples that we have to train our model. While it's typical to use something like an 80-20 or a 70-30 split for our training and testing, where we again are using something like 80 or 70% of our data to train and 20 or 30% to evaluate, how you split your data may depend on the number of samples that you have and how many you need to effectively train your model. Expanding on this, a simple train test split with or without a validation set has a notable weakness. Your test set may not be representative of the larger population. Collecting large data sets can help reduce this problem, but differences in subpopulations, label proportions, and other factors may make it difficult to create a test set that matches the context that you plan to apply your model. If we are trying to predict something like high school dropout, for example, where in a data set of 10,000 students, maybe we have at most 1% or 100 students who dropped out, if we randomly split our data, we could end up with all of the students who dropped out in our training set. Or we might end up with 0.5% of the test set representing students who dropped out rather than the expected 1%. If we want a good estimate of how well our model will perform in practice, we ideally want the test set to resemble that application context as closely as possible. Cross-validation is one method that we can use to address this problem. K-fold cross-validation is an evaluation method that extends the simple train test split to examine how well your model extrapolates to unseen samples throughout your entire dataset. For this method, we first divide the entire dataset into K-folds, typically 5 or 10 in are most common in practice. We'll continue with a 5-fold cross-validation for the example here. Next, we train our model using all but one of the folds. This resembles a train test split, where in the example, we use 80% of our data to train the model, and then we evaluate the model on the remaining 20% in the held out fold. This process then repeats, alternating which fold is used as the holdout set, using all others then as training. And we do this again until each fold has been used as the testing set. When this process finishes, we'll have K sets of evaluation metrics. Basically, we would have trained 5 different models in our example and have 5 different evaluations of how well that model did on each of the held out folds. We can then take an average of these metrics and report this as the overall model performance. This produces a more robust estimate of how well the model is likely to perform, as any variation in test sets is effectively averaged out in this process. There are several special cases to this method that can also be considered. Leave one out cross-validation is an extreme case where the number of folds is equal to the number of samples. This maximizes the size of the training set used each time, but can be computationally expensive, especially if your dataset is large. Stratified cross-validation changes the way that data is folded to try to maintain roughly equal data distributions within each fold to further reduce large variation. This is typically helpful if you have scarce labels, like in our earlier dropout example. Finally, group-level cross-validation is particularly common in educational contexts due to the often natural nested grouping structure of students in classrooms. In this case, data is folded such that no data from a specified group exists across multiple folds. A student-level cross-validation, for example, ensures that each student's data is contained within a single fold. So we are always evaluating how well the model extrapolates to new students, which is often the context in building prediction models. Similarly, a class-level cross-validation would evaluate how well the model extrapolates to new classes of students. The evaluation method used will depend on the intended use case of your prediction model. This slightly changes the research question that is addressed depending on the granularity of your dataset. This matters more when you have multiple samples from the same student in your data. In this case, if you fold your data without student-level cross-validation, you are effectively evaluating how well your model extrapolates to new samples from the same population of students as your training set, which might be the case in certain applications. With student-level cross-validation, you are evaluating how well the model extrapolates to new students from the same general population of classes.